Now we are going to study about the strength of the acid and bases, right? As I told you, the acids are categorized into two categories depending upon their degree of dissociation, that is the strong acid and the weak acid. Similarly, the strong base and a weak base, right? So we are just going to study about the strength of the acid and bases now, that how, like if somebody asks you to derive it in a mathematical order, then how you are going to do that, right? So how I am doing it, see, for an acid, I am taking the acid as an example. Suppose I have the weak acid, that is the acetic acid. I know that when I will dissolve in water, then I am going to get an equilibrium between the acetate ion and the hydroxide ion, right? So if I say that the initial concentration of this acetic acid is C and this concentration is 0, this I am taking that as an initial concentration, right? Now at equilibrium, what I get, at equilibrium, if alpha is the degree of dissociation, right? If alpha is the degree of dissociation, that means the amount of acetate ion produced is C alpha, and similarly the H ion is C alpha. And what we get from the acetic acid, that means C is equal to minus C alpha, that can be written as C1 minus alpha, right? Now I am writing an expression for it, equilibrium constant expression, or you can say that it is the acetate ion, the hydrogen ion divided by the acetic acid and the water. You know that how I have written this. You know what is the logic behind, right? Now I am multiplying this H2O factor with this. What I get Ka. So it is the acetate ion, the hydrogen ion and the acetic acid, right? So this is now the ionization constant for an acid, right? So now I am just substituting the value of this into this. So what I get, this is C alpha, this is again C alpha, and this is C1 minus alpha, right? By solving it, we get C square alpha square C1 minus alpha, right? Here you can see that we can cancel this C with the square, right? So we are left with C alpha square 1 minus alpha, right? If I consider, or it is not a, you can say my opinion for considering the acetic acid, we know that the acetic acid is a weak acid, that means it dissociates up to a very small extent, right? So likewise, in this case, in this expression, I can just neglect the degree of dissociation, considering because it is a weak acid, it dissociates only to a small extent, right? So we can neglect alpha in this case, and after neglecting, what I get is Ka is equal to C alpha square divided by 1, right? If you write 1 or not, you do not write 1, it doesn't make a difference, you know that. So what do I get? Like if I want to know the strength, so I have to get the expression for the degree of the dissociation. So this is what I am doing here. So this is alpha is equal to Ka upon square root of Ka upon C. So this is the, you can say, the degree of dissociation for an acid. So this is how you are going to derive the expression for the degree of dissociation for an acid. For a weak acid, if you want to know the strength of an acid. So by looking at this relation, have you got something strike in your mind? Something has knocked your mind or not? Yes, you are right. It is the same expression in the same way we did for a weak electrolyte. The only difference lies in that it was Ki and here it is Ka. That's it. And even the expression which we have obtained in this case is the similar one. The difference is only this A, that is, it is for an acid, and that degree of dissociation was for an electrolyte. That's it. So as we did in Oswald dilution law, I think you can easily recall it. So this is how you are going to do know the strength of an acid by just calculating an expression, deriving an expression for the alpha A. Similarly, we do it for the base, right? Suppose I am just doing it for the base. It's easy for you to do now, but still I am doing it just so that you should be familiar with this expression as well. So we get this. Right. So in second thing, what we are going to write, we are going to write the law of, you can say, the expression for the equilibrium constant. So that means K is equal to NH4 positive and OH negative divided by NH3 and water. Right, this is the multiplication sign, do not forget, right? So we know that if I multiply this H2O with K, you know that it becomes Kb, that is the ionization constant for a base. So it is NH4 positive OH negative divided by concentration of NH3, right? So now I'm just considering the concentration as I did in this case. Suppose initially it was C and it was 0 and 0. With passage of time, if degree of dissociation is alpha, then at equilibrium what we are going to get is C minus C alpha, the concentration of NH3, and for this we are going to get C alpha and C alpha. So it comes out to be C1 minus alpha. So just substituting this value into this as we did for Ka, what we get? C alpha, C1 minus alpha, right? So if after just solving it, we have this. As we neglected alpha in that case, I think you remember I neglected the alpha in this case, just considering that it is a weak acid, so we can neglect it. So in a similar manner, I am just neglecting the alpha in this case, considering it is a weak base, right? I am not considering, I am just again repeating that it is a weak base, right? So if you are writing a general expression, then consider it, otherwise just write blindly that yes, it is a weak base, so you have to neglect the alpha in this case. So what do we have now? It is C alpha square upon 1, and alpha comes out to be square root of Kb upon C, and it is again for base, so I am writing the subscript B for alpha. So this is an expression that how you are going to do it for the calculating the strength of an acid and strength of a base, right? But now the question comes, if you get two acids now, because this we have done for one acid and this I have done for one base, right? But if you get a question that compare the strength of HCl and H2SO4, so how you are going to do? You know that HCl and H2SO4, that means both are acids, that right? So we need to have the degree of dissociation for an acid, right? So you know that the alpha is directly proportional to the ionization constant for an acid. So in a similar manner, we'll do that. 1 alpha A2 root Ka1 root Ka2. So this is how you have to solve when you get different acids and you just have to compare their strengths. Similarly, if you get a question for a base, so in a similar manner you are going to do for this as well. Suppose this is B2, it is again equal to Kb1, Kb2. So this is how you are going to compare the strengths. I think it is clear to you now that how we write how we calculate the degree of dissociation and how we get to know the strength of an acid, right? Now, one more thing what we get to observe is that we have certain substances in which the acid is present, or you can say in which the hydrogen ion is present, but the hydrogen ion present is more than 1. Like I'll give you an example. Suppose I have HCl. So what information do you get from HCl? It has one H, right? And if I take an example of H2SO4, then it has 2H. And if I take an example of H3PO4, it has 3H. So that means it has the ability to give 1H, it has the ability to give 2H, and it has the ability to give 3H, right? Because they all are giving H ions, that means they all are acids. They belong to a same category, right? So these type of acids are called as polyprotic acids. That means those acids which actually has a tendency to release more than one proton, or you can say more than one protonium ion, that is more than one hydrogen ion, they are said to be polyprotic acid, right? So I'm just writing an expression in a general form for you, how you get ionization constant of acid for them. So I have an acid H2X, suppose, right? So it has 2H, as you can see it is dibasic in nature. It has 2H, it has a tendency to give 2 hydrogen ions, right? But in one go, it is not going to give all its hydrogen ion. In one go, it will give, at a time, it is going to give only 1 hydrogen ion, right? So we say that it donates, it just released 1 hydrogen ions, and we are left with HX negative, again an ionic equilibrium, right? And suppose the value for this expression, the ionization constant for an acid for this expression comes out to be Ka1. Similarly, when we are left with 1H more still in this acid, right? So that means in the second step it is going to give its next H. Now there is no H, so no further reaction is going to take place. And for this reaction, we have Ka as Ka2. Right, so this reaction I have written in 2 steps, but I can write in 1 step as well. So I am writing this reaction in 1 step. So I can write in this way, right? So suppose I say the equilibrium constant expression for this is Ka3. Now how I am going to relate these values? So Ka3 is just, you can say, equal to Ka1 into Ka2. The same way we did for an electrolyte, right? That means if the reaction is occurring in a step, the equilibrium constant for a complete reaction is equal to the multiplication of the equilibrium constant for the different steps. So similarly, I did it for this. The only difference lies, or you can say the only difference between this and that one was that here we have the ionization constant for an acid, and that was the basic equilibrium constant. But still, the equilibrium constant obeys all those characteristics which was obeyed by the chemical equilibrium. That is why the Ka also obeys all those characteristics of the chemical equilibrium, because basically it is a chemical equilibrium constant. But when we are considering for the acid, we are just making it Ka. When we are considering for a base, we are making it Kb. The only difference is that otherwise it obeys all those properties of the chemical equilibrium constant. So this is we have. Now if I compare the value of this, this and this, which value is going to be greater? Do you have any idea? Yes, you are right that Ka1 will be more than Ka2 and it will be more than Ka3. Now what is the reason behind it? The reason is that when you remove one first proton, right, so more is the negative charge, there is more difficulty in removing the proton ion. But as we proceed, the negative charge is decreasing, therefore the release of hydrogen ion is just becoming more easier. So always the Ka1, that is to release the first proton ion, or you can say the first hydrogen ion will be difficult, and likewise its value will go on decreasing. That is why Ka1 will be more than Ka2 will be more than Ka3, because as we move, the negative charge is getting reduced, right? So similarly, the similar thing I can do it for the base as well, because we have many polyacidic bases. What is that? Suppose I see here I have NaOH. What you get to see? One OH. That means it has one OH. So obviously it has a tendency to release only one hydroxide ion. But in this case, we have two OH. So similarly, we can have three, we can have many. So we just write they are polyacidic basic. So any substance which has the tendency to release more than one hydroxide ion, it falls under the category of the polyacidic basic. So similarly, we can have an expression for it similar as I did for the acid. We can do it for that case also, and in that case also the Kb1 will be going to be more than Kb2 will be more than Kb3, right? So this is how you are just going to solve for polyprotic acids and the bases, right? And I think you can recall that Bronsted-Lowry concept as well. As I told you that according to the Bronsted-Lowry, you know that the proton donor is an acid and the proton acceptor is a base. So do keep in mind that every base, a strong base has a weak conjugate acid, and every you can say a strong acid has a weak conjugate base. That is vice versa in that case, right? A strong acid, weak conjugate base. A strong base, a weak conjugate acid, right? So this is how you're just going to compare the strengths, right? Now the question must be arising that what is the factor which is responsible for, you can say, what is the factor behind that makes an acid or a base strong or a weak? So that is only two factors which are responsible. One out of them is strength of bond and the other is polarity of bond. So as we have strong acid and weak acids, likewise we have strong base and weak base. So what are the factors that are making them strong or weak? So there are only two factors which are responsible. One is the strength of bond, other is the polarity of the bond. Now the question arises, what is the strength of bond? That means suppose I have an acid. So if this force of attraction between this molecules, or you can say these ions are weaker, that means the strength of bond is weak. And if the strength of bond is weak, that means it can be you can say broken easily, and if it gets broken, then the release of hydrogen ion becomes more easier. So that means the stronger it is going to be an acid, right? And similarly, if this bond appears to be strong, then that means the bond breakage is not so easy. That means the release of hydrogen ion is not so easy. So that means weaker acid it is going to be proven later when we'll study it, right? So similarly it happens for the base. So I think it's clear that how the strength of the bond matters to make a substance a strong acid or a strong base, or a weak acid or a weak base. It is just the force of attraction between the atoms which are clubbed to form a molecule. So weaker is the force, and more easily it can just donate the H ion or hydroxide ion, and likewise it is going to behave in a strong manner. Now the second factor is the polarity. What is that? Polarity is that, suppose I have an example of an acid HCl. What you get to see in this? We get that chlorine is more electronegative. That means there is a difference in the electronegativity. So that means it is going to attract the shared pair more toward itself, and as a result it is going to acquire this partial negative and positive charge. So that means more polar is the bond, more easier is to donate the hydrogen ion, and the less polar is the bond, or you can say lesser is the electronegativity difference, less polar will be the bond, and the difficulty of the H ion will be more difficult. So weaker will be the its nature, right? So this is how the two factors just make the substance the strong or a weak. So there are only two factors which are responsible. Just keep in mind, one is the strength of the bond. No matter if the bond is between H and A, that means the hydrogen ion or any respective atom which is present along, or whether it is in bases. It is just the strength and the polarity between the atoms which are just present in the molecule of an acid or a base.